This is our ball beam balancer project. In this presentation, we will go over beam design, the sensors utilized, a video demonstration, system modeling, control algorithm, design issues, and the final product. The beam materials used included acrylic, hot glue, and various electrical components. The beam arm was 20 inches in length with 8 inches or 12 inches on either side of the fulcrum. The fulcrum was 4 inches above the base, and the linkage attachment point was 4 inches from the fulcrum. The linkages measured 2 inches in length each, and the servo sat at 1 inch above the base and 4 inches from the fulcrum. The sensors used included a servo, a rotary potentiometer, an Arduino Uno, and a 500mm soft potentiometer.
Alright, potentiometer, we can turn that on and change our set point position. So we're going to set our set point position at 4, 5/10, up to 4, okay, and then Lauren's going to place it on there, and it's going to go to 4, hopefully, and stay there for 20 seconds. Sweet. It's at 15, so once it hits 35, it's been here for 20 seconds.
Before we developed a control algorithm, we modeled the physical system with a series of equations. For this analysis, L is the length of the beam, R is the radius of the ball, and alpha is the angle between the beam and the ground. Here we see a free body diagram developed for the system, where friction is neglected for simplicity. There are two types of motion in this system, translational and rotational. The translational force is defined as mass of the ball times acceleration along the surface of the beam. Rotational force is then defined using the equation for torque, which is moment of inertia times rotational acceleration. This acceleration is equivalent to the derivative of rotational velocity with respect to time. Recalling that omega equals velocity over radius allows us to get torque in terms of linear acceleration. Finally, rotational force is solved for by substituting in the equation for moment of inertia of a solid sphere. A summation of forces is then taken along the axis of the beam. The equations for translational and rotational forces are substituted into this equation, and the Laplace transform is taken. The transfer function is finally developed by dividing the output x of s by the input alpha of s.
To obtain a working ball beam, we were able to manually tune our gain values. Our proportional gain value came out to be 2.3. Our integral gain value came out to be 0, and we had a derivative gain value of 1.5. The block diagram is as follows. A rotary potentiometer is used to set the set point. The soft potentiometer is the location of the ball. The PID controller takes these two inputs and comes up with an angle using the gain values. This angle is the angle of the ball beam, which is converted to the angle of the servo motor, which is then our output. Our Arduino code basically follows the block diagram. It has the KP, KI, and KD gain values, which are used by the PID to compute the output.
We ran into some design issues while working with our ball beam. As seen in the following video, the ball would get close to the desired position, but would oscillate plus or minus an inch from the destination indefinitely. Our track was also curved due to the acrylic being bowed, causing the ball to have issues balancing even when our track was completely horizontal. However, we were able to fix our oscillation issues by lowering the output limits of the PID controller. Having higher magnitude angles caused more oscillation, whereas a smaller range of angles allowed for the ball to balance quicker by making smaller adjustments.
Alright, so now we're going to randomly change this. I guess not randomly, we're going to pick -1. Why is not focusing? Yeah, 4, 3, 2, focus please. 1. That's going to go to 1. Start that. So once it hits 30 seconds, you got that. Boop. 30. And marker. That's it, it's a 1/2 inch of one. Alright, sweet.
Future tuning can be done to decrease the time it takes for the ball to balance on the beam. Better hardware and more power can improve the performance and response of the ball beam. Also, construction of the ball beam can be improved, like placing the linkages near the end of the ball beam to get a better modulation.